Okay, so we'll get started. Quick announcement. The reason why I have a video camera is because tomorrow there is no formal class. What we're going to do, don't start crying. What I'm doing is I'm conducting some fitness assessments on forest firefighters in the gymnasium from starting at 9 o'clock in the morning and running probably till about 2 or 3 in the afternoon. So because of that, it runs into our lab time. What is being distributed right now is a copy of the lab that you are to do then on your own time. So instead of like not doing anything at 2 or 4 o'clock, depending on what time you have lab, you could do that lab. What I am going to do is as soon as I'm complete with the wildland firefighters, I am going to go to M113 and I will be there doing work. And if you want to come and do the lab there in the lab and I can give you assistance, then that's your opportunity. Also on Friday from 8 to 10 and on Friday from 2 to 4, I'll be in that lab. I'm going to send out an announcement later this evening on Blackboard to announce this. And why I'm videotaping it is because I'm missing my other section's lecture, so that I'm going to post this video online. So if you make any smart comments, they'll be caught in memorial. Maybe we'll post it on YouTube or post it on Vine. Is there a way you can do that? So you do it for fun? Okay, so we'll get started and we're going to try to plow through. Now a lot of this stuff is going to be basically tying in some of the concepts that we've touched upon already within our previous lectures, because we're talking about measurement of work, power, and energy expenditure. And this is chapter 1 of your textbook, page 16 to page 26. As always, for some reason I have to put this on. There we go. There we go. So we'll do some announcements. Anybody know what movie? No. Say anything. Thank you. Say anything. John Cusack. Back in the day when John Cusack made good movies. Don't forget you have a midterm exam next week. Now the midterm exam will take place on Thursday, either at 2 o'clock or 4 o'clock, depending which section you're in. So what we'll do next week on Wednesday is we'll do a review session. What I recommend is going up until then, review through your notes, figure out where you're having difficulty, because the review session will basically be, here's the format, here are the rules for the policies, procedures, and then what specific questions you have, or let's work through some sample problems to help you understand the material better. Normal caveat, if you're going to be away from the exam, you need to contact me within 24 hours of the start of your exam time. You need to provide official documentation as to why you were away, such as a severe illness or accident, or whatever the case may be. And also you need to write the exam the first day back at campus. So just throw that policy out there right now. Also, student services for learning strategies. So if you do need, say, help with test taking, then you can approach Cindy. Her extension is 5373. And they're in the library, so basically if you're not sure, you need some help or assistance with studying, or whatever the case may be, go to the library, to the student services, and they'll be able to provide you with assistance.
Will they provide you with like a tutor?
You can sign up for a tutor. And if they don't have, like, you have to sign up in advance for a tutor, so they won't have somebody right there. But if you need tutoring, there is tutoring for free, peer tutoring for free. So it would have been a student who has taken this course and gotten good grades, and then they get paid and you don't have to pay them.
Oh, really?
Yeah.
Ooh, that's nice.
There you go.
So you go to the library and do that?
Yes.
Okay, I'm going to go right after this class.
Oh, yeah? I'm definitely going to post this on mine soon. That's exciting right there. So the objectives, as always, is basically your checklist for, do you understand this material? There is some material that's been posted that is not within your textbook, starting with this slide, physics. So we are going to deal with some physics. So some of what we discussed this week will be based on physics and math. I'm sorry about that, but not really sorry. Okay. So units of measurement, first off, you need to appreciate that we use a metric system as opposed to the imperial. Well, you should hear what math says about you. We use a metric system as opposed to the imperial system, right, with pounds and miles, what they use in America. With Canada, we use a metric system, kilograms, grams, meters, those units of measurement. And that's what we try to standardize in, and also newtons and joules as opposed to kilocalories. So In Canada, of course, being to the cultural giant that is the US, we get a little bit mixed up because we measure speed and distance in kilometers, but most people measure their weight in pounds and their height in feet and inches. So we're just like schizophrenic when it comes to that stuff. Work itself, so this is out of your textbook. Work is basically force times distance. That's what work is. That's the definition of work, as opposed to what you do when you graduate and make money. In which case, work equals paycheck minus taxes. So in international standard units, work is measured in joules, force is measured in newtons, and distance is measured in meters. So the example is, you lift a 10 kilogram weight at a distance of 2 meters. So if I had, say, a 10 kilogram weight, and I'm lifting it up, 1 meter, 2 meters, well, 1 kilogram equals 9.81 newtons. So 10 times 9.81 newtons equals 98.1 newtons. And 1 newton meter equals 1 joule. So basically, this would be 1 newton meter. This would be 2 newton meters. So up to here, 1 meter would be 98.1 newton meters, or joules. And this would be 2 of those. So this would be 196. So 2 times 98.1 equals 196.2 newton meters, or 196.2 joules. Makes sense? Clear so far? It doesn't get too tricky, and some of the tricky stuff that we do get to, you've already done. So there we just show the math. 98.1 newtons times 2 meters equals 196.2 newton meters, or 196.2 joules. Coolio? Everybody knows how many pounds in 1 kilogram? Do you remember? 2.2. 2.2, yeah. So it's a good number to remember because, again, in Canada, right, how much do you weigh? I weigh 156 pounds. What is that in kilograms? I don't know. Now you do. Power is basically how fast you can do this. So we take force times distance divided by time. So if I lift the 10 kilogram weight this far, I'm using less power than if I do this rather quickly. Right? If you have less time, the number stays bigger. So power is in watts. So we take work in joules divided by time in seconds. So the example is if you're performing 20,000 joules of work in 60 seconds, so that would be equivalent to, say, a workout work set, a weight, and it might take you up to a minute to perform a set. Just a side note, according to the American College of Sports Medicine guidelines, most sets should be performed within 90 seconds if you're working on musculoskeletal function. So in this case, we're doing it within 60 seconds, so basically we would take 1 watt equals 1 joule per second. So 333.33 joules per second equals 333.33 watts. And the way that we get there is 20,000 joules divided by 60 seconds equals 333.33 joules per second, or 333.33 watts. Right? Now watts, most people recognize watts in terms of maybe wattage of a light bulb. You know, the projector we have has a 500 watt light bulb. These lamps, they're fluorescent lamps, maybe you use a 25 watt light bulb, or if you have the old style incandescent light bulb, it's a 100 watt light bulb. You may also run into this when you're on an ergometer. You're pedaling at a certain pace, and if you remember this, we did basically resistance times distance times RPM, or frequency, right? So let's say you're using a resistance of 1 kilogram, the distance is steady, and the frequency is 60 RPM. Then 1 times 6 is 6. 6 times 60 equals 360 kilogram meters per second. And if we divide that by 6.12, so if we divide that, 360 divided by 6.12 equals 59 watts. So I know everybody's like, wow, this is fascinating math. I love it. Awesome. Okay, measurement of work and power. So ergometry is the actual measurement of work output. So here, these two people that are smiling, look at, he's so happy. And he's so concentrated. He's like, I should have shaved this morning. She's kind of cute, but so is he. I don't know. I'm torn. Here we see the individuals in the red shirts, right? They're not in Star Trek, so they're not going to die. They're measuring the guy with 5-day stubble, and they're measuring ergometry. It's a measurement of work output. Whereas opposed to what he's sitting on is an ergometer. It's a noun. It's a thing. So a bicycle would be an ergometer. When you're pedaling on a bike, we're measuring ergometry. We're doing measurement of work output. Common ergometers that you're going to see, we don't have a picture of one from our lab, but the steps in our lab would be an ergometer, right? The Monarch's bikes that we have, also treadmills are ergometers, and also arm ergometers, and 3 of these 4 images are taken directly from your textbook. The reason why I substituted this one in is because this is standard height, whereas opposed to the one in the textbook is one of those Reebok steps, and you adjust it, and well, how much work are you doing? So we have standard height. The key thing is you want to have your machines calibrated. These bikes cost over $2,000, and the reason is because we can calibrate them very accurately, which reminds me how to calibrate them again. With the other ergometers, you may have seen these swimming flume, so it's like a treadmill for swimming. So it shoots a current past a person, so they're stationary, but because the water's moving past, they're swimming in the water. You have a rowing ergometer, right? Standing kayak ergometer, or a horse ergometer, right? Like they're actually measuring volume of oxygen uptake on a horse. And horses are very aerobic type animals. So they have all types of ergometers, and they've measured VO2 on all types of animals, all the way from mice all the way to elephants. Yeah, so it's kind of cool. Direct calorimetry. So if we want to measure directly how much energy we're using, basically we measure how much heat you're producing, because your bodies produce heat. So most people have seen the movie The Matrix. Yes. Right? It talks about how we're just really copper tops to the robots. Well, we produce heat. Our bodies produce heat. If you recall, what percentage of conversion of food energy into ATP gets converted to heat? Do you remember? I'll give you 2 out of 3 guesses.
60?
66%. About 66%, right?
I was going to say 66. Then you just stop it.
Yeah, sure, blame you. So you take food stuff, and you combine it with oxygen to get ATP, and from the ATP you get heat, but you also get heat from the working of the cell. So it's commonly measured in calories, but what you see on the cans and like on food labels are actually kilocalories. So 1 kilocalorie will equal 4,186 joules. So you think back, 1 set of exercise took about 20,000 joules, right? And 4,186 joules. So basically in that set you burn 5 or 6 calories. Not a whole lot of caloric expenditure, depending on the intensity and all those other things. Time for Mythbusters episode with our guy, what's his name and what's his name? The amount of heat, this is the technical definition of a calorie. The amount of heat required at a pressure of 1 atmosphere, so that's at sea level, to raise a temperature of 1 gram of water, 1 degree Celsius. And specifically, 1 calorie is how much it takes to raise 1 gram of water from 15 to 16 degrees Celsius. Okay, everybody got that? That's right. So we're looking at raising 1 gram of water from 15 degrees Celsius up to 16 degrees Celsius. And that's at standard pressure, so sea level. So therefore, normal body temperature is about 37 degrees unless you're running a fever or like you're with a certain someone, raise your body temperature a bit, because you're both bowling. So this is a myth that we've seen out there. If I drink 100 grams of water that's at 17 degrees Celsius, well, 37 minus 17, so 37 your body temperature, minus 17, the temperature of the water, times 100 grams of water is 2,000. Therefore, I'm going to use 2,000 calories just to warm up that water. Makes sense, right? And I'm going to lose weight. 2,000 calories. That's the caloric expenditure requirements of half the people in here. Well, sorry, you're all super fit, so you all probably burn like 5,000 calories a day. Yeah. But the thing is, this is false. The caloric content of food is actually given in kilocalories. So for example, you have a can of Coke, which says it has 160 calories. That's actually kilocalories. That's 160,000 calories. And it's not that your body is actively going to spend a lot of energy heating up that food. Like, that energy is getting burnt anyways. Your stomach's warm anyways, so that can of Coke's going to get warmed up fairly soon anyways. I mean, sometimes there are side effects, right? You're a kid, you eat too much ice cream, and then what happens? Right, you feel like your head's going to implode on itself. But it's actually false. So, I mean, drinking cold water is not an effective way to lose weight, unless you're, say, drinking 5 gallons of cold water right before you head to Mandarin buffet and you're too full to eating, in which case maybe it would help with not gaining weight. So, diagram of simple calorimeter, direct calorimetry is basically we put you in this big chamber, and we have air flowing into the chamber, and we have air flowing out of the chamber, and we have a circulating jacket of water. Now, if you're not aware of this, water is very effective at absorbing heat. So you may have experienced this if you ever go camping or to the beach, and you're there all day and all night, and it starts to become evening, and you get into the lake or the body of water, but usually it's a lake, and the water is what compared to the air temperature? At night, warm, right? Because it's retaining all that heat from the daytime. So we just measure the temperature difference. We measure the temperature of the air going in, and we measure the temperature of the air going out, and the difference is basically, it's warmer because you're producing heat. And if you're producing heat, we know how many calories you're burning. The only problem is with this method is, what would happen if we were to put, say, a treadmill or a bike in? So we want to measure exercise calorimetry directly. What happens when we put, say, a bike or a treadmill in here? What do you think the bike or treadmill will produce? Also, heat, right? The motor on the treadmill or the resistance on the bike, resistance mechanism of the bike will produce heat because of an artificial elevation of. So this is very effective for, say, at rest, or if the chamber is big enough during exercise, like maybe skipping, but maybe jumping jacks or something like that. But even then, you get heat. Like if you have somebody who's, you know, marching on the spot, but maybe they're a little bit heavier, and then you get like the thigh rubbage, and there's friction, right? So something to think about. So what we do is we do indirect calorimetry, if you can pronounce it. So it's measurement of oxygen consumption as an estimate of aggressive metabolic rate. And we learned this before, right? Because we said for every liter of oxygen, about how many calories are you burning? Do you remember? I'll give you maybe high 4 or 5 guesses. 4. Yeah, somewhere between 4.7 and 5.05. Right? So what it says is you combine food stuff, so, you know, it's February, it's Black History Month, by the way, but more importantly for most Canadians, it's our time to celebrate our favorite addictions, sugar, gambling, and caffeine. So let's roll up the ring. So you go to Tim Hortons, you get your coffee, you get your double-double, you're taking in calories, you get, you know, while I'm here at Tim Hortons and I stood for 20 minutes in the line, so I might as well get my apple fritter also, or, you know, like Boston cream or vanilla dip. And you take those food stuffs and you combine with oxygen, you produce heat, plus carbon dioxide, plus water. But we've seen this, right? We've seen this from oxidative burning of the, aerobic burning of the food stuff. So basically, for about every liter of oxygen, you're burning approximately 4.7 to 5 kilocalories per liter of oxygen. And part of your lab activity is going to involve that. You're going to do it in partners, and one of you is going to exercise and then figure out, hey, how many liters of oxygen you're consuming, how many calories are you doing? And we call it open circuit spirometry. And the reason why we call it open circuit, so give me an example of a closed circuit. Can you think of a closed circuit in your body?
The heart.
Yeah, the heart. Very good. Not even giving any hints. Good job, Jeff. Good for you, Jess. All right. See, brilliant. It's going to be recorded for posterity. So the heart is a closed system, unless you know you get some road rash or you're playing hockey, or because say good blood, play hockey, right? But this is open circuit spirometry. So what we do is we have you breathe in room oxygen, which is about 20.9493% oxygen. And we have you breathe it out, we analyze what you breathe out, and also what you breathe in, we take the difference, right? So if you breathe in 21%, you breathe out 16%, it's the difference of 5%. And then we can figure out, well, 21% in, 16% out, 5% of the oxygen is being used. That's a basic concept. Just a picture of the new leaf system, which we have in our labs. We're hoping to have a VO2 demonstration later on this semester, so I know I have one second-year student who's volunteered, but we'll canvass you folks and see if any of you want to volunteer to have this done. And the system we have is for teaching purposes. So basically what happens is our subject, the victim here, breathes air in, and then when she breathes it out, this samples the volume of air going out and the percentage of carbon dioxide and oxygen. It does basically a measurement of how much oxygen she's consuming while standing still on that treadmill for the photographer, or walking. So the example, subject weighs 60 kilograms, about 132 pounds, ventilation, so they're breathing in and out 16 liters of air per minute. They breathe in 20.93% oxygen, to make it easy, they breathe out 16.93% oxygen, so what percentage of oxygen are they using? Say 21 minus 17. 4. Right? 4%. Right? And what we do is we basically do 60 times 4%, or 60 times, right? 60 times 0.04, because what we're doing is we're doing 60 liters per minute times 20.93 minus 60.93, which would then equal 60. And 4% is the same as 0.04, which equals 2.4 liters per minute of oxygen. Is that absolute or relative to VO2? Absolute. Absolute, yeah. Not relative to the body weight, right? You guess first. Just saying. So for kilocalories, if we figure out that, right, they're burning a range of 4.7 to 5.05 kilocalories. So if you want to do it quickly in your head, just to make it quick, do it by 5. Most people can multiply, except for your math lovers, haters. Haters gonna hate though. I don't know what haters hate. Like, what math ever do you need? Just, you know, in algebra, just tell x. Listen, math, find x. Like, get over it. Find your own x. So if we do, you know, 5, 10, 15, 20, 25, right? So 2.4, you notice 10 calories right there. So 2.4 times 5 calories equals 12 calories per minute. If we do 12 times 30, that's 360 kilocalories in a 30-minute session. And again, we go back to what I just explained to you in the lab session, which is this becomes significant because, you know, you can say to your client, listen, that 160 kilocalorie can of Coke, that's a big deal. And you had it with a Snickers? You believe that, like, Brady Bunch commercial with, what's like the ugly Mexican guy who's a senior? Have you seen that? Okay. I just saw it yesterday. Anyways, the guy's like in his 70s, but he looks good. Machete, he was in that movie. Yeah. So Marsha has a Snickers bar, say 200 calories, and a can of Coke, 160 calories, and she's going, well, what's the big deal?
It's 250. For Snickers.
For Snickers? Okay, but just for, maybe she didn't eat it all. Maybe she gave some to Danny, because he's like kind of mean looking. Right? So she has 360 calories, and you say, well, you know what, you could have saved yourself half an hour of work right there. Right? So this is where kilocalories becomes significant. Or the opposite end is where they say, don't want to lose weight, and you say, well, you've done half an hour of light aerobic activity, so let's put 360 calories back into you. So if you have someone who is using, now we look at milliliters of oxygen per kilogram per minute, and now hopefully this stuff is starting to stick, because this isn't the first time that we've talked about this, and that's one of the goals that I'm having, is that by repeating this stuff, either you'll fall asleep because it's a good cure for insomnia, or, right, so Leon right there, Victoria's like, why did I come today? You're supporting action, okay? And Jordan. But hopefully by repeating this stuff, it sinks in and it starts to go, oh, I'm making the connections, right? So you take 2.4 liters, but you have to convert it to milliliters. So you multiply it by 1,000, so it becomes 2,400 milliliters of oxygen per minute. Divide by their body weight. So right now they're working at a rate of 40 milliliters of oxygen per kilogram body mass per minute. So, you know, a good example is, we take someone like Greg, rather large individual, we take someone like Heather, rather small individual, and let's pretend you weigh twice as much as you. And if you're both working at 2.4 liters of oxygen, who is working at a relatively higher VO2?
Great.
And why Greg? Because we took absolute divided by body weight, and he weighs more.
Yeah.
She's smaller.
She's smaller. She's working at a higher relative body weight. Because think about it, if we took 2.4, so 2,400 divided by 120 would equal 20, right? Like a bigger individual at the same absolute VO2 will use fewer per kilogram.
Is there giving less ink or smaller?
Well, Heather would be using more because let's look at it this way. If I have 50 students on this side and 100 students on this side, and I give out $2,400 to 50 students, and I give out $2,400 to 100 students, per student, which side gets more? 24?
Heather.
Yeah, that side, Heather's side. $2,400 per 50 students, each student gets more money than you sat. So you sat in the wrong side of the room. This is kind of a diagrammatic representation. Remember those equations I had to do, right? 3.5 times 0.1 times speed plus 1.8 times speed times grade. And going, why am I learning this? Well, what this shows is this shows the relationship between walking and running speed and the amount of oxygen being used. Now, there's kind of a missing piece here, and that's because the equations are wildly inaccurate. So anything below 150 meters per minute is inaccurate for the running equation. Anything above 100 meters per minute, the walking equation becomes inaccurate. And if you actually use the walking equation or the running equation, what you find is that when someone is walking at 90% of their VO2 reserve, they're walking faster than they would be if they're running, unless you set the elevation up really high. But there are reasons behind that, because basically, let's say you had to go somewhere. Let's say you're in a plane in northern Canada, you're flying along, plane crashes, you're there for a couple of weeks, cannibalize the pilots because you saw it live in the in-flight video. You're like, okay, I know how to do this. Go for the glute max, biggest muscle mass, right? And then you decide, I need to get out of here because 3 people just died on me, and so you decide caloric reservation. How am I going to be most efficient? You're going to be most efficient if you're walking, right? If you're running, and so many people say, what's better, walking or running? Well, when it comes to caloric expenditure, everything else being equal, running you burn more calories. So there is significance behind it. This has been posted on Blackboard, correct? Yes. But basically it just shows a breakdown of all the components with the equations, and you can expand that on your Blackboard document or save the image. But the assumptions are, first off, we've got some assumptions, and you know what to say. When you assume things, it means that you don't really know what's going on. But we assume that right now your resting metabolism, for every minute that you're sitting there, for every kilogram of you, you're using 3.5 milliliters of oxygen, right? And how many METs is that? How many METs is resting metabolism? 1. It's the loneliest. The 3.5 is also low. But we don't know, right? Some of you may be consuming 3.47 mils of oxygen, some of you may be consuming 3.53. We really don't know. But we're assuming resting metabolism is 3.5. Next, we assume energy is, efficiency is constant. So who do you think will be more efficient swimming in a pool? Michael Phelps or me?
You.
Thank you, suck-ups. You got a little bit of brown in there. No, Michael Phelps, of course, right? Like, who do you think is going to be more efficient at sprinting? Usain Bolt or me? Yeah. Usain Bolt, right? So we assume, though, efficiency is constant. That everybody's running on the treadmill 6 miles an hour, 2% elevation is using the same amount of oxygen. But we know it's not true. Also, we assume that age-predicted max heart rate is your actual max heart rate. But we know this isn't always true. For example, I know my max heart rate, I haven't actually measured it directly in a while, but I know my max heart rate is probably higher than the age-predicted max heart rate. Why? Because I can run on the treadmill for 5 minutes at my age-predicted max heart rate. And I can tell you, I'm not an aerobic machine. I'm not like one of these marathon runners that can do that. So, there you go. Trust me, I'm not a marathon runner. Some of the other assumptions, so there's a horizontal component. When you walk or run, you go horizontally. And then also there's a vertical component, like you have to run up a hill. So we assume that for every 1 kilogram of U that travels 1 meter, so travels 1 meter horizontally, you use 0.1 milliliters of oxygen. And that's where the 0.1 in the equation comes from walking, right? There's 0.1 of oxygen. With the running, we assume you're less efficient, so to move that 1 kilogram of U 1 meter, you use 0.2 milliliters of oxygen. And this is why we say, for flat surfaces especially, walking, you're more efficient because you use less oxygen. The vertical component, walking, we assume for every meter you go up, you use 1.8 milliliters of oxygen. And for running, we assume you use 0.9 milliliters of oxygen. Now the reason why, any idea why you're more efficient vertically when running? Momentum, what's the difference, what's the big technical difference between walking and running? Not necessarily. Have you ever seen power walkers? Power walkers like hip machines, and they're like,
Both feet.
Yeah, so walking, running, walking, 1 foot is always in contact. Running, you're airborne, it's high impact. So you're already going vertical, and that's why it says you're more efficient in the vertical component.
Oh, no, I wasn't.
Okay, I'll stop listening.
I meant because I couldn't.
So if you break down your equation, you can see then resting component, and this is part of it. It's not just using equations. I mean, if I ask you a question in the midterm with these equations, I'm going to give you these equations. But if you understand what it's talking about, you better understand what you're doing. It's not just like, oh, math, I hate math. That's fine, you can hate math. Hater's gonna hate, but like try to learn and appreciate it. It's just like a foreign language, right? Learn another four-letter word. But you have the resting component, you have vertical component, and you have the horizontal component of your equations. So, the assumptions of leg cycling. So power or work rate equals resistance times distance times frequency. Resistance is in kilograms. Distance is a distance of flywheel travel. So for every revolution of your leg, those bikes in the lab, we assume the flywheel, the big wheel in front, goes 6 meters. And frequency is just how fast you're pedaling. If you want to convert it to watts, you divide by 6.12 like we had before. And total oxygen demand, first off, the unloaded spinning. So so that basket weighs ½ kilogram. If we take that basket off and you're spinning against no resistance, we assume you're consuming 3.5 milliliters of oxygen per kilogram body weight for every minute that you're just spinning, no matter how fast or how slow. Of course, we're assuming, right? That's an assumption. The external load, if we add resistance to that, you have to use more oxygen. And then also your resting metabolism. What's resting metabolism? How many mils of oxygen per kilogram of U per minute are you consuming at rest?
3.5.
3.5. Right? So again, break down the equation. Really, the horizontal component is unloaded spinning of the bike. The vertical component is when you add resistance. And the resting component is 3.5. And that's why we have 3.5 over here, 3.5 over here, not just 7. To remind you, unloaded spinning, resting metabolism. So you're walking on a treadmill at 3.6 miles per hour, 3% elevation. What's your relative oxygen consumption? What you need. Oh.